What's up, guys, and welcome back to some more science talk, even though it had been a long time, guys, since I made my last video back in November. If you want to go ahead and go check it out, make sure you check out my channel. It'll be Quantum Mechanics, Season 4, Episode 2, so whatever, guys. So today I'll be talking to you guys about General Relativity, Season 4, Episode 3 of Science Talk. So, what General Relativity means is it's like two parts of relativity, right? When I mean two parts, the General Relativity is one of them I'm going to be talking to you guys about today. So, this is a theory published by Albert Einstein back in 1915, if you guys have ever been wondering. And yes, 1915 was an important time for Albert Einstein. And this is the certain description of gravitation in modern physics we know of today. So, general relativity specializes special relativity, another thing published by Albert Einstein. But, however, since I'm going to be talking to you guys about general and special relativity, alright, so let's get along with special relativity first. So, what I want to talk to you guys is, in 1905, a man named Albert Einstein had created something called on the electrodynamics of moving bodies. That was his third paper of the year that he created papers. Or you could say in German, der Electrodynamic Betriebliche Körper or whatever. I don't really speak German, so letting you guys know, I don't really speak German. But on June 30th, 1905, that is when this man was creating his paper. But that was published until about a few months later on September 26th. But this really reconciles, or I should say, it takes over Maxwell's equations. Now, if you guys want to know Maxwell, that is a man named James Clerk Maxwell. That guy was a very awesome scientist. I really trust sometimes of his awesome stuff that he created back then, right before his time of Albert Einstein. He also helped out on quantum mechanics as well. And again, if you want to check out the quantum mechanics, check it out on my channel, right? And yes, guys, you know what? So whenever I was thinking about this just a second ago, I was thinking about how did the general relativity overprice the special relativity. Well, basically, guys, it is just the same relativity skills. So if you guys want to know science, right here is me. Or you can trust Bill Nye and all those other people. Alright, but that's basically why I created Science Talk to tell you guys about science and all that stuff. So, yeah, so you know what? But special relativity is like the general accepted and experimentally well confirmed physical theories of all time, but this regarding the relationship between space and time. Space is up and specifically space. Time is what I was saying. Space-time is like any mathematical model that combines space and time. So, that is what I wanted to tell you for just a sec. Though it's a little bit off topic here, so. But, however, since I am smart, guys, Well, I did wanted to create history talk for a reason, but anyway, so let's get on topic. So now, whenever I was thinking about, the theory of relativity, in special relativity, it is like a well-confirmed physical theories, or scientific theories. But not all theories are true. So, but yeah, that special relativity is always true. But yeah, this implies a wide range of consequences, which may have been experimentally verified, including length contraction, time dilation, relatively mass, the mass energy equivalence. Now, if you guys want to check out, the mass energy equivalence video, go ahead and go check out on my channel as well. Alright, so, and by the way, my YouTube account is Lalone Boys. Some videos were made about my brother and all that stuff. So, but yeah, we need more subscribers. So if you want to subscribe, do that right now. If you're watching this video, make sure you subscribe on my channel. So, yeah, what I was thinking is that it also has to deal with speed of light and relatively of stimulation, or whatever you say. It's like stimulation with relativity. So, and I want to describe to you what those things mean. So, first of all, length contraction. It's like the phenomenon of a decrease in length of an regular object, as measured by an observer. And remember, you gotta have an eye to observe. So, I just wanted to get you a key reference too. So, well, but this was just traveling at non-zero velocity relative to the object, as I was talking about. So, next off, time dilation, which is a difference of elapsed time between two events as measured by observers either moving relative to each other or differently situated from a gravitational mass or any masses. So, that is what time dilation is. Now, specifically, what else be the relativic mass? Has to be like mass in special relativity. Now, scientifically, the relativistic mass is what I was talking about scientifically. What you guys could say is mass in special relativity. Alright? So, this incorporates the general understandings from the concept of the mass energy equivalence. Now, also, the mass energy equivalence, obviously, I told you guys about that, so check it out on my channel. Alright? So, now, I did want to describe to you guys about the universal speed limit, as I feel like that's a little bit too complicated for me, but relatively of stimuli, or whatever. So, this would definitely mean the concept that distant stimuli, whether two spatial separated events occur at the same time. But it is not absolute. But it does depend on the observer's reference frames. So yeah. Alright, so that is special relativity. Alright guys, give me 1 sec to pop up general relativity. It'll be just 1 sec, so now what we guys talk about now, starting right now, is general relativity. Now, I know I described a little bit about it, but I'm going to describe it to you more today. So, right now. So, now, you know what? I would say general relativity, this generalizes special relativity. But it also does Newton's law of universal gravitation, however. So, while this provides an unfound or should say, unfiled description of gravity as a geometric property of space and time, or space-time, scientifically. So, in particular, the curvature, a curvature is like any loosely related concepts in different areas of geometry. So, this is directly related to the energy and momentum of whatever matter and radiation are present. But this relation is specified by the Einstein field equations, again, filled by Mr. Albert Einstein. So, but yeah, that is like a system of partially differential equations, or PDE. Now, whenever you're thinking about Einstein, you better be thinking about PDE. So, I want to do you guys a favor. I want you guys to do me a favor and remember PDE, right? If you guys want to learn about science and all that stuff. Now, I'm not talking about mathematics specifically, but I'm talking about physics specifically. So, yeah. That is what I want you guys to remember. So, but some predictions of general relativity differ significantly from those of classical physics. But I do want to say this, but in my next video, I'll be talking to you guys about classical mechanics. Because, yeah, I talked to you guys about quantum mechanics, but I haven't talked to you guys about classical mechanics, which dates back to like 1600s to 1700s and all that stuff in the past. So, that's why I'm going to be talking to you guys on the next video, whenever I get a chance. So, but yeah, this does have to deal with classical physics when you're talking about general relativity. But this especially, or to say, it differs it. But that comes especially concerning the passage of time, the geometry of space, the motion of bodies in a free fall, like when you decide to go ahead and go fall down on something. Hopefully you land on a trampoline. And the propagation of light. So, examples of these such differences include gravitational time dilation, or whatever you said. So, gravitational lensing, the gravitational redshift of light, and the gravitational time delay, or the Sharpo delay. So, the predictions of gravitational relativity have been confirmed in all these times of observations and experiments to date. So yeah, there were a lot of tests on general relativity. So, but although these are not the only relativistic theory of gravity, however, it is the most simplest theory whenever you're talking about this guy named Occam's razor, or specifically William of Ockham, which is dated back to classical times back then. If you're talking about philosophy, which I know I ain't gonna be talking about philosophy today, but however, that is the most simplest theory that is constant with experimental data. However, unanswered questions remain. The most fundamental being how general relativity can be concealed with the laws of quantum physics to produce a complete and self-constant theory of quantum gravity. Alright guys, so that is all I've got, alright? And I do want to recognize Happy Martin Luther King Jr. guys, or I should say, Happy Martin Luther King Jr. Day guys, and make sure you subscribe, comment in the comment box below. Make sure you guys also like the video and subscribe, like I said. Alright guys, that's all I've got, so I'll check you guys out tomorrow, or no, not tomorrow. I'll check you guys out on the next video. Take care, everybody.